Students, welcome to the next topic. We are discussing about the torque on a current loop placed in a uniform magnetic field. So here in the figure you are observing a current loop PQRS which is carrying the current in the clockwise direction indicated by the red arrow, which is placed between two pole pieces of a magnet, such that in between the two pole pieces of magnet we have a uniform magnetic field B. The loop can be divided into four branches or four arms: arm PQ, QR, RS and SP according to the direction of the current. Now, when current will be running in the each of the branch of the loop, then each current we can consider each branch as a current carrying conductor placed in the external magnetic field of the pole pieces of the bar magnet. This means that each conductor or each branch of the loop will experience some amount of definite amount of Lorentz magnetic force. So in this case, if the current in the loop is I and the sides of the loop are B, which is the length of the loop, and A, which is the width of the loop, and theta is the angle between the normal to the plane of the loop and the direction of the magnetic field, then we can calculate the force on all the four arms using the force expression for force on a current carrying conductor, which is equal to ILB into sine theta. Now if we now take a look at the arm PQ. Arm PQ has magnetic field directed from north to the south pole. The current is carried from P to Q and the angle between the current and the magnetic field is 90 degree. So in this case, if we apply the expression ILB sine theta, length here is equal to length of the arm PQ, which is equal to B. The expression reduces to IB into capital B. Similarly, if we calculate the expression for arm RS, it will have the same force acting on it, F equal to IB into B, because here B and I, they are still perpendicular to each other. Only difference here, the current is running in the downward direction from R to S. Similarly, the force on arm S and P and Q and R, it can also be calculated. Here the force on arm SP and QR, it will be equal to I into length of arm A into the magnetic field B into sine of the angle between the direction of the current and direction of magnetic field. Here you can see that N is the normal or perpendicular to the surface of the loop and B is the direction of magnetic field, which is making an angle theta. This means that if this total angle is 90 degree, out of which this much angle is theta, then this angle is equal to 90 minus theta. So over here the equation for force on arm QR, it will be IAB into sine of 90 minus theta. Sine 90 minus theta is cos theta, so this will be equal to IAB into cos of theta. Now this expression for arm QR, which is IAB cos theta, is equally valid for the arm SP. Now if we apply Fleming's left hand rule, according to which the index finger, if it is pointing in the direction of magnetic field, middle finger points in the direction of the current, then the thumb will give us the direction of the force acting on the current loop, the current carrying conductor. In that case, we observe that the force on the arm PQ, it will be acting in this direction. That means normal to the loop pointing in the inward direction, while it will be acting on the arm R and S normal to the direction of field and the current, but pointing in the outward direction. If we apply the Fleming's left hand rule to arm QR, at any point on the loop, the force it will be acting in the vertically upward direction, and for arm SP it will be acting vertically in the downward direction. Now if we compare the forces IAB cos theta for arm QR and SP, they are not only equal in magnitude but they are exactly opposite in direction. That means their line of actions are exactly anti-parallel to each other, so they have a common line of action, so they exactly cancel each other. But if you look at the line of action of the forces acting on PQ and RS arm, although forces are equal and opposite, but their line of action are different, because of which these two forces acting on PQ and RS arm, they form a couple, a torque, due to which the loop will start rotating in the anti-clockwise direction. So this torque which makes the loop to rotate in anti-clockwise direction, we can calculate this torque with the expression torque is equal to either force multiplied by the perpendicular distance. So either force, we already know the value of the force is I B into B. We just need to calculate the perpendicular distance, for which we are using this figure in which we have indicated the direction of the inward force and direction of the outward force. This is the distance between the two forces, which is equal to the width of the loop, that is A. This is the normal to the plane of the loop and direction of magnetic field, which are making an angle theta with respect to each other. If this angle is theta, then this, if we draw, this is the line of action of the force, this is the line of action of the outward force, then this angle will also be equal to theta. So if we draw perpendicular from one line of action to another line of action, we want this much distance, which using simple trigonometry it will be equal to A sine theta. So the perpendicular distance becomes equal to A into sine theta. So the net expression for the torque will be IAB into capital B into sine theta. This is the expression for torque if there is a single loop, single turn of wire. But if we have n number of turns, then the total torque it will be equal to N IAB into B sine theta, which can further be written as, if we multiply A and B, A is the width of the loop, B is the length, which is nothing but the area of the loop. So this expression for the current loop can also be written as Ni into capital A into B sine theta, where capital A is the area of the loop. Okay, so at last we can write this product NIA as the magnetic dipole moment of the loop. So final expression for torque will be equal to tau is equal to MB into sine theta, or in the vector form we can write it as tau is equal to M cross B. So this torque which acts in the anti-clockwise direction will rotate the loop in the anti-clockwise direction. Special cases: if theta is equal to 0 degree, if theta is equal to 0 degree, torque will also be equal to 0. This is the case when the plane of the loop is normal to the direction of the magnetic field. If theta is equal to 90 degree, then the torque acting on the loop it will be equal to NIAB, or you can also write it as MB, which is the maximum torque acting on the loop. This is a case when the plane of the loop is parallel to the magnetic field. At last, remember some important points. This torque which we have calculated is independent of the shape of the loop, because in the expression for the torque experienced by the current loop, we have tau is equal to MB sine theta, okay, and which is further written as NIA and B. So it depends upon the area of the loop, so it is independent of the shape of the loop. Second thing, for a given perimeter, because circle has a maximum area, this means that if we have a planar circular loop, then a maximum torque will act on the planar circular loop for a given current. At last, third point, if the magnetic field B makes angle alpha with the plane of the current loop. Earlier we have considered that normal to the surface of the plane of the loop makes angle theta with the direction of magnetic field. Now we are saying that if the magnetic field is making angle alpha with the plane of the current loop, this means alpha is the angle between the direction of the magnetic field and the direction of the current, then we can say that theta plus alpha is equal to 90 degree and theta will be equal to 90 minus alpha. So in this case, tau will be equal to NIAB sine 90 minus alpha, which will give us final expression tau equal to NIAB into cos alpha. In uniform magnetic field, net force is 0, but torque will keep on varying between 0 and maximum, as we had discussed in first and second point. In non-uniform magnetic field, force will not be 0 in this case, because both arms PQ and arm RS will experience unequal force, because magnetic field acting on both of them will also be unequal in magnitude, and torque again varies between 0 and non-zero. So this was the expression for torque on a current loop in a uniform magnetic field and some of its results.